So, Leo?
Yes.
Could you share your screen, please? And you have 15 minutes.
Can you see my screen now?
Yes.
Okay.
Go ahead, please.
Okay, thanks. So, hi again. My name is Leonardo Garcia, and today I'm going to present you this work that I am researching during my PhD. It's called the evolution of the relativistic jet through the magnetized medium produced by the fusion of two neutron stars. And my advisors are Diego Lopez Cámara and David Lazzati. So let's start with this. So this brief introduction that I have, what is a GRB? Well, I think that all here knows what is a GRB, so I am going to focus in the short GRBs that have this 1090 minor equal to 2 seconds, and the isotropic luminosity it goes from 10 to the 47 to 10 to the 43 arcs per second, as we can see here in this plot, in which we have this isotropic luminosity in this label in the redshift here. So in this plot, we can see the isotropic luminosity for the GRBs, short GRBs, sorry. Also, the short GRBs have this theta jet of between 5 and 25 degrees, as we can see here in this plot from Berger 2014. And the progenitors of the short GRB are the neutron star mergers, and these neutron star mergers we have here one of these simulations of a 1 year simulation in which we have this neutron star merger. As we can see here, we can see the plant view of this merger, and here we have the meridional view. This is a plot of the logarithmic density, and in this study they search for different equations of state plus different mass ratios for the neutron stars, and saw what was the result of these mergers. So this is quite important because we can have different initial conditions for different simulations. So this will be important in the talk. So the next point is that the post-merger medium effects have been studied by several authors, as we can see here in these references. And also from the Cholfi simulations, we can see that there are a lot of magnetic field. So the magnetic field in the medium is need to be studied. So in this plot, we can see that the magnetic field goes from 10 to the 12 to 10 to the 16 Gauss. Here is the in logarithmic scale. And this is what we are doing in this work. We are searching for the effects of the magnetic field in the jet evolution. So the methodology that we are doing is that we have this density of the medium from Cholfi, the pressure and the magnetic field. So we took these profiles from the Cholfi 2017, the simulations that I showed you before. We map it into the 2.5D RMHD Pluton code, and then we can inject this a relativistic jet with these properties that we have here. Luminosity of the jet 10 to the 50 arcs per second, aperture angle of 10 degrees, initial Lorentz factor of 5, and an infinity Lorentz factor of 400. So here we have this diagram in which we can see how is the injection of this jet. So we have several boundaries, reflection and reflection, outflow for the ones these two parts. Also, we can see that we have one distance to the compact object. This distance to the compact object is 200 kilometers, because we are not doing GR simulations. So we are only taking into account the special relativity. So also we have two different distributions of magnetic field, one that is only poloidal and one that we have the two components, poloidal plus toroidal magnetic field. So once that we have these, the profiles from the density and pressure, we can add the magnetic field at the medium, and then we can try with different values of beta. As you remember, beta is the ratio between the gas pressure and the magnetic pressure. And with that, we can see the effects of the magnetic field, the weak magnetic field or the stronger magnetic field. So here we have this table that is is a reference that for the models that we will do in some time, in some point. And now I am only going to present you three models for this table that are labeled in the next slides. So let me show you this. This control simulation that we have here. I am showing you this logarithmic, density map in logarithmic scale in grams per cubic centimeter. We also can see the isocontrols of Lorentz factors between 1, 5, and 15 for the different colors. And you can see the evolution of this jet at the edge of the domain. Okay, so once that we saw this control simulation, now we can see different times of this simulation. So here we have this initial condition, and we can see how the density is decreasing in the R component. Also, we can see when the jet is at t equal 4 × 10⁻² seconds, and it's really small. And then I took this time at t equal 8 × 10⁻² seconds, and you are going to see why in the next slide. So this is the final shape that I am taking to compare with the other simulations. And as you can see here, we have the well-developed jet with this core with a velocity of 5 of the Lorentz factor of 5, and we have this like bubbles of 15 Lorentz factors. So with that, we can compare now with the simulation with magnetic field, once that we have this morphology of the jet in the control case. I remember that in this case, we don't have magnetic field. So in this part, we can see in the left, the control case that I showed you before. And in the right, we can see the one model that is with the poloidal magnetic field, and the beta of this medium is equal to 0.5. So as you can see here, we can see like a few differences between these two jets. The first one is that we have the jet that is in the magnetized medium evolves in a larger distances, a larger distance. And also we can see that these bubbles of Lorentz isocontours of Lorentz factors are like a kind of bigger, but the shape, the morphology, it's almost the same in the sense that we have like a well-developed jet, and the cocoon is not also really big. It's maybe narrower than the control case. So only to be sure, I put this line to see the distance that records that evolves the control case, and the distance that it's bigger the poloidal case. So as you can see here, with in poloidal distribution, the jet travels a larger distance. So also we have here in this part, we have it's a
5 minutes.
magnetic field map. Pardon?
5 minutes.
Okay, so here we have this magnetic field map in which we have this in logarithmic scale between -1 and 12 Gauss, 10 to the 10 Gauss, 10 to the 12 Gauss. And as you can see here, this part is not magnetized in the jets, in both jets. And also we can see that when the jet is traveling into the medium, the jet core is getting magnetized, and also the cocoon is getting magnetized. So the jet core is slightly more magnetized as the medium magnetic field increases. It's you can see how a good eye. And here we have this plot in which we are seeing a comparison between the distance that the balls each jet. So the magnetized models present a difference in the jet evolution, as you can see here. The magnetic field, the jet that evolves in a medium with magnetic field equal to 0.5 evolves more than the jet with beta equal 5.0. And the jet with beta 0.75 evolves more than that case, but less than the 0.5 case. So it's what I was saying before. This is still is work in progress, and we also need to do more quantification in this part. So as the conclusions, the jets that evolves in a medium with lower beta travel larger distances than the jet which evolves in a medium with higher beta. So remember that a lower beta implies that the magnetic field is bigger. So the magnetization of the jet and the cocoon increases with beta, and also the magnetic field produces an important effect in the evolution of the jet. So this is all that I have, and also for the future work, we are going to do some resolution studies to see the convergence of the simulations to be really sure. Also, I am going to add the colloidal plus toroidal magnetic field distribution, and we are going to do the quantification of the jet and cocoon properties. All of these points are in the short term. In the medium term, we are going to do the simulations in a medium with velocity, and we are going to try with different mediums. So this is all that I have. Yeah, thanks.
Thank you, Leo. Questions? Raise your hand, please. In the meanwhile, could you tell us how you can distinguish observationally between a GRB with magnetic field or not, and without it? Is there some feature that you could see? I mean,
Yeah,
for example,
maybe
duration.
one of the
plateau.
features is the polarization. Other could be the time delay between the signals of the gravitational wave and the GRB, and that could give us an idea of the magnetic field inside of this dynamical ejecta. But I'm not sure what other features we can see. It's one of the points that we need to study really.
Yes, definitely. Well, if there are no more comments, thank you again, Leo. And we can move on to the next talk. Gerardo.